Okay, welcome back. So we'll be doing this problem. So as I read the problem, for once I'm going to do the figure here so you can see the way I approach the solution of the problem. So steam enters a converging divergent nozzle. So what does converging mean? Converging means that basically it's going to be going toward one area in common. Okay, so it will be, then this could be the cross section. Imagine a wind tunnel. Okay, so this is cross-sectional area, and then it's going to diverge. But let's say our test section is along this line. So what we know is that steam, so we know the state, enters a converging divergent nozzle operating at a steady state with P1. So on this side we have P1 equal to 40 bars and T1 equal to 400 degrees Celsius and a velocity of 10 meters per second. The steam flows through the nozzle with negligible heat transfer and no potential energy. So that means basically heat transfer Q is 0. In other words, it means that all this system is insulated and there is no potential energy equal to 0. At the exit, the pressure P2 is 15 bar and the velocity is 665 meter per second. The mass flow rate, so basically the mass flow rate in and out is equal to 2 kilograms per second. Determine the exit area of the nozzle in meters square. Okay, so basically what we need to find is A2 over here. Alright, so this figure might not be needed, but I want to try to give you as much information as possible, but let's see what happens over here. So if we do so we have lines of pressure, so let's do the TV diagram. So it looks like we go through two lines of constant pressure, one at 15 and the other one at 40. So let's say this will be P1 40, P2 15, and let's see, try to complete this figure as we do the problem. Okay, maybe we can go right away to this one. So let's see, this is steam at 40, so P1 equal 40 bars. Okay, so if you go to the tables, table A6, let me zoom in a little bit, you see that they give you 4 in megapascals. Okay, so we know that 1 bar is 100 kilopascals, which means that 40 bars will be 4 megapascals. Okay, so we can go to the table for, let's see, 4 megapascal. Do we have it? So here goes up to 3.5 on this side. So this is table A6, 4, and let's see what happens at 400. We have a value of V equal to 0.07343. Okay, so I'm just looking for the figure. So really you see it's way above the saturation. So let's say it would be somewhere over here, we're also going to need the information, but for now, let's just do this. V1, this is T1. So you know T1 is 400. So let's put those values. So from table A6 at P equal 4 megapascals and T equal 400 degrees Celsius, what do we have? So we have V1 is equal to, so let's look at it again, V1 equal to 0.073 0.07343 0.07343, and this would be cubic meters per kilogram. And let's just put right away the value H1, which I think we're going to need. So that value from the same table will be at 400, 3,214.5. So 3,214.5. Okay, so we know where state 1 is. Okay, so all right, let's go back to this page over here. Let me zoom out. Okay, so what is the equation we have at our disposition? We know the first principle of thermodynamics for the control volume. So I'm just going to do very quick the figure over here. So remember that I really like a lot of figures, so this would be our control volume. So this is really our control volume, okay? Here we know P1 equal to 40, T1 400, V1 10, P2 15, V2 665. We need to find A2, and we know that the mass flow is 2 kilograms per second. Okay, so the first principle will be what? Heat transfer minus the power for the control volume plus m dot H1, neglecting the potential energy, that will be 0. So we have the enthalpy plus the kinetic energy, and that should be equal to m H2 plus V2 velocity to square over 2. So in the problem, they tell us that heat transfer can be neglected, and here there is no work done on the system or by the system, so this will also be 0. So basically in here we can cancel the m's, and everything basically is known. H1 from the table, V1 we know, V2 is also known. So the only unknown is really H2. So if we solve for H2, what do we get? So let's say H2 will be equal to H1, and now I'm just going to move this V2 over here. So we'll have H2 equal to, so H1, H2 equal H1 plus 1/2 of V1 square minus V2 square. right? So let's do the numerical application. So we have numerical application. So we have H2 is equal to what? H1 was equal to 3000. I'm just copying from this page. 300, 214, and this should be kilojoules per kilogram. So 3,214.5 kilojoules per kilogram plus 1/2 of V1 is 10 square minus 665 square, and this should be meter square second square. Okay, so be careful here with the units, because basically what's going to happen is that we know that 1 Newton is 1 kilogram meter second square. So this is F equal ma, 1 Newton equal mass times acceleration. But now is that 1 kilojoule is equal to 1000 Newton meter. So now if you do this, you can see that we have the kilojoule here, we have the kilogram here, so this Newton cancel with this Newton, this meter combined with this one to cancel this one, and this second square cancel this one, so we're left with kilojoules per kilogram. Basically, we need to divide this value by 1000. So if you do the calculation, 2,993.4375 kilojoules per kilogram. Okay. Let me zoom out for a second. All right, so why is this important? Because now we know that the mass flow M is equal to the volumetric flow rate divided by the specific volume. So this is really equal to A V1 at the inlet V1 equal to A V2 specific volume 2. So basically mass flow 1 equal mass flow 2. So A is the area, V is the velocity at the inlet divided by V1, and we should have the same thing at the outlet. So we know M, we know the velocity V2, and now using H2 and the tables, we can find what is the value of V2, and then we just need to solve for A. Okay? All right, so let's go to the tables. All right, so let's see what we know about 2. We know the pressure is 15, so we need to look at table again A6 at P equal 15 bar. So far that's what we know, and we also know that H, we need to look at H equal to 2,993.4375. Okay, so 15 bar would be 1.5 megapascals. Okay, so let's see on the other side. So we are out of luck because the table give, let me zoom in, the values for 1.4 and 1.6. So the best thing we can do is to create our middle table for this one, but just for the values that we're interested on. So let's see, we know that H is 2,993. So it's over here. So let's see, at 1.4 that corresponds between the temperature of 250 and 300. Okay. And on the table of 1.6, the same values give us 2019 and 335. See if I can zoom even a bit more. Okay, so look at the 250 here, H 2927.9, 3040, 250, and here we have 2919.9, 3035. Okay, so all right, so let's do all those calculations here. So we know at P equal 1.4, we have, and T, so let's see if we can do it this way, 1.6. Okay, so at T equal 250, T equal 300. So I'm also, so we need the V and the H. So at 1.4, we're gonna have V equal to 0.16356, and we're gonna have that H equal to 2927.9. Okay, now 1. So this is, oops, okay, write that up, but maybe this should be on the same temperature, so forget about this for a second. Okay, and now so it would be 1.4, and we have the other H will be H equal to 3040.9, and V equal to 0.18233. HV. We do the same thing at 1.6, we get 2919.9, 3035.4, 0.141980, and 0.15866. Okay, so remember, between 250 and 350, this will be the value 0.14190 is here, 0.15866 is here, and then 2919 is here, 3035.4 is here, and we did the same thing for the 1.4. So now actually what I need to do is just that for P equal 1.5, all I'm doing is actually just adding those two values together divided by 2, okay, right in the middle. So this would be for 250, T equals 300. So after you do the calculation, you have that H here equal to 2923.9, so that should be this H plus this H divided by 2. We do the same thing for the other H, so this H plus this H divided by 2 give us 3048.15. With the V's, we do exactly the same thing, we get 0.15273, 0.170,495. All right, So now we need to do the interpolation. So, I mean, by now I hope you are good for the interpolation, but just for this case, I'm just going to redo it again. So remember that you always want to put on the y-axis what you're looking for, and on the x-axis what you know. So let's see, you know 0.1, 2, so for H1, so this would be, let's call this one here, no H1, so this would be HA, VA, HB, VB. Okay, let me zoom out a little bit. All right, so let's see, for VA, this would be VA, and this would be HA. Say would be a point here, A. Then we have VB, which is higher, and HA is also higher, so let's say we are here. This would be HB. So we do a linear interpolation, and we want to find the value. Oh, okay. I say something. So this is V. So sorry, this is VB, VA, HA, HB. Sorry for that. Okay, so we need to find the value here. So what we're trying to find is V2, and we know H2. So basically we have what? V2 will be equal to what? VA plus the slope of this curve, which is basically the tangent, so how much it goes up per unit length, so that would be VB minus VA divided by HB minus HA. Okay, and then that distance over here would be what? H2 minus HA. So if you do the numerical substitution, you will find that V2 is equal to 0.1627 cubic meters per kilogram. All right. So now finally, remember we know that the mass flow is equal to the volumetric flow rate, which basically that means A2 V2 divided by specific volume. So from here we can solve for A2 by looking at this equation and this equation. We have that A2 is equal to what? Mass flow times specific volume divided by the velocity. So by doing the numerical application, we have that A2 will be equal to what? 2, let me use the units here to double check, kilograms seconds, times the specific volume that we found to be equal to 0.1627 cubic meters per kilogram divided by V2, which is 665 meters per second. So personally, before I even do the calculation, I first check the units. So we know we need to get units of what? Square meters, okay? So we see here that the kilogram will cancel with a kilogram. this second cancel, and we have cubic meters divided by meters. It gives meters square. So if you do the calculation, you get here 4.892 10 to the minus 4 meters squares. Okay, so you see these problems, conceptually they're not that difficult, but sometimes you have a lot of algebra involved, which makes it easy to do some type of mistake on the way. So this will be the end of this video. Thank you.